Swayam Prabha. Digital India. Educated India.
Here we are in a chemistry course. We are writing a lot of mathematical expressions, but as we had said in the introductory video itself, mathematics is the language of science, and we cannot do anything related with quantum mechanics without using math, and the math we are using is very simple. And before going further, let me just share something with you. We are many of us are scared of calculus, and I used to be, I still am, and we are writing a lot of equations in like del y, del 2 del something 2, so on and so forth. But have you noticed something? We have hardly done any calculus so far. What we are doing really is some very simple algebra. We are doing algebra with operators which contains derivatives and all. Okay. So, it is really not as scary as it looks. So, I thought I will just say it once so that students who have taken this course with a lot of enthusiasm do not get scared off. There is nothing to be scared of. If you can handle chemistry, if you can understand reaction mechanisms, if you can work out sequences of organic reactions, this should not be difficult for you. Okay. There is an atrocious joke that I usually say in this context, borrowed from a very senior colleague, but since this is going in public domain, I will not say that. Let us just say this, there is nothing to be afraid. We are not doing any mathematics that is beyond us. Let us have faith in us and we will be fine. Okay. With that brief message, let us continue with what we are doing. We have developed the classical description of quantum angular momentum. From there we have built a quantum mechanical description as well. Okay. And we have written down the expressions of, well, we have not really written down the expression of L square operator, but we said that it is something in spherical polar coordinates. The operator of utmost importance that we will have is this minus IH cross del phi, which is the Lz operator. And what L square operator is we will see in a moment. Alright. So, now with this background, knowing what angular momentum is and knowing how we handle angular momentum in quantum mechanics, let us go ahead and learn some important properties of angular momenta in quantum mechanical systems. Of course, remember we are talking about operators so far, so there must be wave functions also. So, these operators will operate on those wave functions to give you the value of angular momentum or its square or one of its components and so on and so forth. So, first we are going to talk about L square and Lz operators. This is the L square operator as promised, minus h cross square 1 by sin theta del theta operating on sin theta del theta plus 1 by sin square theta del 2 del phi 2, and the moment you see this you will remember perhaps that we have already encountered this when we talked about rigid rotor, right. And in fact, you would remember that this modified just a little finds its place in the as the Hamiltonian of the rigid rotor system, okay. And Lz also is something that we know. Now we are going to discuss a very interesting and important and perhaps leading to some intriguing discussion of these operators, and that is written in the headline. We will see that L square and Lz actually commute. We are going to show it. What is the meaning of commutation? That means the sequence of operation does not matter. Okay. You take a function, make Lz operate on it, get another function, make L square operate on that function. okay, you get some answer. Then go back to that original function, make L square operate on it, perhaps it is best if I write. I am not very sure if I have written it later, but I will write anyway. Which color ink is the good? This. So let us say I have some function f. I have some function f. I make Lz operate on it. So I will get some function maybe f dash. So I make L square operate on it. I get say some function f double dash. Okay. Here dash and double dash do not mean first and second derivatives, just some function. So what we have got here is that f double dash is equal to L square Lz f. Now what I am saying is that if I reverse it, make L square operate on f, we get something. Now I am running out of dashes. So maybe I will write f subscript dash, and now I make Lz operate on this f subscript dash, I get say f subscript double dash, that is equal to Lz. Oh, this I have written incorrectly actually, sorry about that. So I will just erase this and I will take it from here. So Lz operates on f to give you f dash, L square operates on f dash to give you f double dash, then we will say f double dash is equal to, start from f, Lz has operated on it first, then L square has operated on it. So L square Lz f, that is f double dash, and here L square operated first on f to give you Lz f subscript dash, then Lz operated on f subscript dash to give you say f double subscript double dash. This f subscript double dash is, start from f, this time your L square operates on f first, then Lz operates on the new function. So what we are saying is, you will see that f double dash equal to f subscript double dash. Okay. That means that would mean that they commute. Just erase this because I do not exactly remember where things are going to pop up in the screen. Yeah, so this is Lz. Let us see if they commute or not. So first we will take the this sequence, make Lz operate on f first, then L square will operate on it. So what do I get? You have f is a function, Lz is minus IH cross del del phi, that operates on f, then this L square operator operates on the new function. How do I go about it? Well, f is an arbitrary function in theta and phi, of course. First of all, I can take this minus IH cross out because it is a constant. So I have one minus sign here, another minus sign here, they give me minus 1, sorry, they give me plus 1, minus into minus, and the constant I get outside is IH cross cube, IH cross cube comes out. Next what I do is I take f in. So here I get del f del phi. Now look at the second term, this is when I operate L square on the whole thing, I am going to get 2 terms, right. I will have to handle 2 terms. I will take the second term first. Here I have del f del phi and I am operating it twice with respect to phi. So what do I get from here? I will get del 3 del phi 3, sorry, del 3 f del phi 3. Is it clear? Here I have del f del phi, I am differentiating it twice with respect to phi. So I get del 3 f del phi 3, that is the second term. And what about the first term? This one goes here. So basically I have del f del phi, I have to differentiate it with respect to theta. So, here I am going to get del 2 f del theta del phi. Okay. So, this is what I will get. L square operating on LZF gives me IH cube multiplied by 1 by sin theta del theta sin theta del 2 f del theta del phi plus 1 by sin square theta del 3 f del phi 3. Now, I want you to pause the video for a minute and work out the next one. I want you to work out what Lz L square f will be. Of course, in that case we just alter the sequence of the two operators. Please do it for yourself and tell me what you get. I mean, you cannot tell me what you get, unfortunately, not right now, but see for yourself what you get. I hope you have got this answer. You took f in here and there, and this del phi and del phi 2 once again give you del 3 f del phi 3 in the second term. So, multiplied by the same 1 by sin square theta, and del phi of del f del theta is once again del 2 f. Well, del phi del theta, whether you write del 2 f del phi del theta or whether you write del 2 f del theta del phi, does not matter, it is one and the same. So, I hope you have figured out by yourself that you get the same expression L square Lz f and L square, I made a mistake here, peril of copy paste. So, let me again correct by hand. This was L square Lz f, what I have here is Lz operator comes first. So, you see we can make mistakes while writing too many things. Please make sure that if there is a mistake you are aware of it and you correct it, okay. Should not learn something is wrong. Okay. So, we got L square Lz f and Lz L square, they are the same expression. Okay. Why do I need f? Because I mean, how do I work with operators unless they operate on some function, that is why. Okay. So, this is what we have got. Oh man, I have done it time and again. So, L square Lz f minus, just write it all over again, Lz L square f is equal to 0, okay, which means L square Lz minus Lz L square is equal to 0. Okay. Just reverse the sequence of operation, you get the same answer. So, you subtract the resultant functions, you are going to get 0, right, because you get the same function no matter whether you make Lz operate first or whether you make L square operate first. Okay. So, L square Lz minus Lz L square equal to 0. Okay. So, remember this is a mistake. So, L square Lz minus Lz L square equal to 0. This is how you write it. This cannot be a mistake, fortunately. So, this is how you write it. The commutator is equal to 0. Commutator means this L square Lz minus Lz L square. It is written as L square hat comma Lz hat in third bracket. That is how you denote commutator in quantum mechanics. Commutator just means two functions a and b, ab minus ba, that is the commutator. You write it as a comma b. So, L square and Lz commutator is equal to 0, right. So, the commutator is 0, the operators commute same on the same thing. Now, the question that is logical to ask after so much of discussion is, so what? And alright, commutator is 0, and how does it matter? To know how it matters, we need to go back to the basics of quantum mechanics a little bit, take a holiday, brief holiday from angular momentum and talk in terms of two general operators, and that is what we will do now. Perhaps we should have done it at the beginning, but we really wanted to get on with the show without going into too much of nitty gritty. So, we will do it now that we need it. Now, we are going to learn the answer to that question, so what if it commutes. So, to do that, let us say A hat is an operator, B hat is an operator, and phi A and phi B are two functions. Let us say, to start with, phi A is an eigenfunction of A with an eigenvalue of A, phi B is an eigenfunction of B with an eigenvalue of B, and let us say that A and B commute, right, commutator of A and B equal to 0. Okay. Now, we can write like this, AB minus BA operating on phi A equal to 0. Why do you have to write phi A? Why not phi B? You can write phi B, who is stopping you? I am writing phi A. You can do the other one. In fact, I encourage you to do the other one and convince yourself that you get the same result. Okay. AB minus BA operating on phi A gives you 0. Now, we now know the sequence of operations. If I write AB phi A, that means B operates on phi A first and A operates on the resultant function, and if you write BA phi A, that means A operates on phi A first and then B operates on it. So, A operating on B phi A minus B operating on A phi A gives you 0. Then we already know what A phi A is, right. A phi A is the eigenvalue A multiplied by phi A. So, we can write that A operating on B phi A minus B operating on A phi A is equal to 0. So, that can be rearranged to A operating on B phi A, and we take this B hat term on the right hand side. So, that minus sign goes. Moreover, remember we are using linear operators. So, an operator operating on a wave function multiplied by a constant gives you that constant comes out and the operator operates on the wave function. Well, in case you did not understand what I said, this is what it means. It means B operating on phi A multiplied by phi A, remember A is a constant, is equal to A multiplied by B operating on phi A. Okay. A operating on B phi A is equal to A multiplied by B operating on phi A. Now, will you agree with me that this is an eigenvalue equation? Eigenvalue equation in what? Eigenvalue equation in B phi A. See, I can write this B phi A as psi. This B phi A I can write as psi. What is the equation we have got? We have got A hat operating on psi has given me A multiplied by psi. We have got our good old eigenvalue equation, and eigenvalue equation in B phi A, psi is equal to B phi A. Okay. So, B phi A is an eigenfunction of A. Moreover, what is the eigenvalue of B phi A? Yeah, psi is equal to B phi A, right. So, eigenvalue is A. So, B phi A has the same eigenvalue A for the A hat operator as phi A. Okay. What is the eigenvalue of phi A for A hat operator? It is A. What is the eigenvalue of B phi A? That is also equal to A, that is what I am saying. Eigenvalue is the same. Then we can write that B phi A is equal to C phi A. Okay. Let me now erase what I had written earlier, because the next thing might actually pop up there. So, see, A operating on phi A is equal to A phi A, that we have started with. Now, what is A operating on C phi A? This is what I was talking about when I said something about linear operators. What is A hat operating on C phi A? That is going to be C multiplied by A hat phi A, right. C will come out, and now what is A phi A? That is again A multiplied by phi A, small a multiplied by phi A. So, you get Ca multiplied by phi a, you can write it as Ac multiplied by phi a. Okay. So, you get this since you have the same eigenfunction. You see C phi a has the same eigenfunction as phi a itself for a hat operator, and that is what holds exactly for b hat phi a. That is why it is abundantly clear that b hat phi a is equal to C phi a. Problem with quantum mechanics is that sometimes we lose our way while we meander through so much of mathematical manipulation. I hope we have not lost our way now. Your advantage is that you can always go back and replay the video. But what I hope you can see easily is that b phi a is equal to C phi a. This is again an eigenvalue equation. So, what are we saying here? We are saying that phi a, which is actually an eigenvalue of a hat, sorry, phi a, which is an eigenfunction of a hat, is also an eigenfunction of b hat. Herein lies the significance of commutation. Phi a is an eigenfunction of b hat if a hat and b hat commute. Okay. So, this is one of the golden rules of quantum mechanics. Operators that commute have a common set of eigenfunctions. Okay. Please make sure you understand this before going further. As I said, it is very important that we do not lose our way in the maze of mathematical manipulation. It is very important that at the end of the day, if you forget all the mathematics, the physical insights sink and stay with us. Okay. What we have learned from this is that for commuting operators, there are common sets of eigenfunctions. What does that mean? It means that associated properties, the property associated with A and property associated with B, can be determined simultaneously. This is the most significant physical outcome of the discussion we have had. Associated properties with the two operators can be determined simultaneously, and that should remind us of something that we have again studied in higher secondary. We know that x and px, position and momentum, cannot be determined simultaneously with any certainty, right. That is uncertainty principle. Where does that come from? It comes from here. X and px actually do not commute. I leave it to you to work out, to read it by yourself. It is there in all standard physical chemistry books. X and px do not commute, you get something like IH cross. That is why x and px cannot be determined simultaneously. What is the meaning of determining simultaneously? That means you should have a well defined eigen function for a hat operator, well defined eigenfunction of b hat operator. A hat is associated with some property, b hat is associated with some property. If they have a common set of eigenfunctions, that means these eigenvalues small a and small v can be determined precisely at the same time from the same functions. Remember how quantum mechanics works? The information, whatever information is contained in the wave function, can be brought out by applying the appropriate operator, the operator associated with that physical quantity. So, if the wave function knows the answer for the value of that property, it will spit it out as the eigenvalue. What we are saying is that if you have a simultaneously, if you have a set of eigenfunctions for two different operators, that means you have eigenvalues for the two corresponding properties. So, the two properties can be determined simultaneously. Very, very important and profound quantum mechanical concept, something that is very central to quantum mechanics. Okay. So, we are very happy that L square and Lz commute. So, L square and Lz can be determined together, is not it? They have same set of eigenfunctions we said. So, we can determine L square and Lz together. Now, think what we have done in rigid rotor. We have always talked about the total momentum from L square, and we have talked about z component of angular momentum. Why? Because we can determine these two together, because L square hat and Lz hat are commuting operators, they commute. Okay. This is a very important take home message, and this sort of tells us why is it that we always talk about Lz and L together. The corollary that should come out is that why do we not talk about Lx and Ly? Okay, we know L, we know Lz. So, it will be so nice if we can find out Lx and Ly as well. Actually we cannot. That is where uncertainty sets in, because I have not worked it out myself, it is worked out in Pillar's book to some extent, and you can work it out yourself now with a little, it is a little tedious, that is all. But just believe me when I say that Lx and Ly, Ly and Lz, Lz and Lx do not commute. So, Lx and Ly commutator is IH cross Lz, that is very beautiful result, right, because this is what is used in things like NMR spectroscopy to find out the different components of electrons nuclear spin. Ly and Lz commutator is IH cross into Lx, Lz and Lx commutator is IH cross Ly. Okay. So, you cannot determine the x component and y component together. If you try to do that, I mean you will not get anything. So, a corollary to corollary question that can arise is that, okay, we understand that. So, we understand that you can determine total angular momentum and z component of angular momentum simultaneously. We also understand that you cannot determine x component of angular momentum and z component of angular momentum simultaneously. But can we determine L square and Lx simultaneously? Can we determine L square and Lz simultaneously? The answer is yes, we can. L square and Lx actually commute, L square and Ly actually commute. Lx and Ly do not commute with each other, Ly and Lz do not commute with each other. So, first point, we can determine any of the components and total angular momentum together, but the moment we do that, the other two components are not defined. Remember, L square, capital L square is equal to Lx square plus Ly square plus Lz square. So, if you have determined say Ly square, then you also know Lx square plus Lz square, but from there you cannot find Lx square or you cannot find Lx or Ly separate, you will not be able to separate it out. That is from uncertainty principle, okay, because Lx and Ly themselves do not commute. Okay, that you can replace x by y, y by z, answer will remain the same. Why do we always talk about z? First, it is convention, we always like to define z as a unique axis. Second is, it makes our life so much simpler. You have seen that the operator in spherical polar coordinates for Lz is so simple, and for Lx and Ly it is quite complicated. So, our life is simpler if we do this, right, that is why. Okay. So, this is what we have, that you cannot determine the components, two components of angular momentum simultaneously. You can determine the total angular momentum and one of the components simultaneously. Great. Now, with that understanding, let us conclude this part of the discussion with something really nice and something that we sort of skipped, giving a hand waving argument while talking about rigid rotor. I am talking about why is there an upper limit of magnetic quantum number. To do that, let us work with Lz operator, L square operator and the spherical harmonics, the wave function for rigid rotor. We will get the same wave function for hydrogen atom later on. So, now we know that these two operators commute, right. So, why do not we do this? We will make Lz operate on the spherical harmonics. This is what we get, and of course, del phi will operate only on e to the power im phi and will give me im, I and I give you -1, -1 plus 1, you will be left with mh cross, we know this. And what we can do of course is, we can, before we do that, we can bring this polynomial in cos theta and normalization constant out, because as far as phi is concerned these are all constants. So, this is what we get, yeah, IH cross Nj Pmj cos theta comes out multiplied by Im multiplied by Em phi, that finally gives me H cross m multiplied by the spherical harmonics. Okay. We are familiar with this. This is the eigenvalue equation for Lz. Okay. We know this already. Now let us make Lx square operate on it, Lz square. Let us find out what Lz square is. Okay. What is Lz square? I do not need an operator for it because I know the eigenvalue. So I just square the eigenvalue, that is what I will get. Do I square the wave function as well? No, please do not. Okay. It is not as if you are squaring both the sides. When I write Lz square, I means I make Lz operator operate on the wave function twice. So this is your wave function, you take this and make the Lz operator operate on it once again. What do you get? You get another H cross multiplied by m, right. M here remember is magnetic quantum number. So you get H cross square m square. Okay. Please do not think that I have squared it like some number or something. Okay. Square of operator means operating twice. Okay. So we have Lz square and we already know what L square is. So what we will do is we are going to subtract this Lz square from Ly square, okay, from L square. I will subtract this Lz square from L square where L is total angular momentum, this is what we get. So we can simplify this a little bit, we can write L square minus Lz square operating on y function of theta phi gives me this minus you can neglect, that is a typo again, H cross square multiplied by j into j plus 1 minus m square multiplied by y theta phi, again an eigenvalue equation. How have I got this eigenvalue equation? By taking the eigenvalue equations of L square and Lz square, subtracting them from one another. Okay. That has led to another eigenvalue equation in which the operator is L square minus Lz square, eigenvalue is H cross square multiplied by j into j plus 1 minus m square. Now see what is this operator L square minus Lz square? We briefly mentioned this a little while ago. Will you agree with me if I say that this operator is Lx square plus Ly square? Because the total angular momentum operator L square, we had said this at the beginning of our discussion previous module, this is actually L square plus y square. So L square plus y square operator has an eigenvalue of H cross square multiplied by this. Now we come to an again simple but important to understand concept. Can Lx square whatever the value is, can it ever be negative? No, right, because square of the x component of angular momentum. We may not be able to determine it, but it is a real quantity. So its square will always be a positive number. What about y component? Same thing. So will you agree with me if I say that Lx square operator, Lx square plus Ly square operator must have a positive eigenvalue, real positive eigenvalue, yeah, because it is a sum of two positive quantities. Lx square can never give you negative quantity because Lx itself is a real quantity, it is not an imaginary quantity. So this has to be greater than or equal to 0. You see that we are there, which means j into j plus 1 has to be greater than or equal to m square, or I can simply say that mod m has to be less than or equal to j. Okay, I can just neglect this j, this one to get rid of this square. Okay. Here we now understand why is it that there is an upper cap to the modulus of magnetic quantum number m. Mod m is less than or equal to j, this is where it comes from. So to summarize, we have learned that if operators commute, then the properties that they stand for can be determined simultaneously. What we have not done is that this non-commuting operators which have properties that cannot be determined simultaneously, that leads to uncertainty principle, that I have left for you to do as self study. We have learned that total angular momentum operator, sorry I missed the crucial angular word here, and one of its component, these are these operators are commuting. So, these properties are determinable simultaneously, but if you take a pair of components, they are not determinable simultaneously. And finally, we have learned how this leads to an upper limit of magnetic quantum number. I hope you have found this discussion on angular momentum very interesting and fruitful. There is more to angular momentum, but once again we do not want to lose our way before in all this maze of what seems like mathematical manipulation. So, we will take another holiday from angular momentum after this. We will go on and discuss something that we are familiar with, that is hydrogen atom. Then while talking about multi-electron atoms, perhaps if we feel it is required, we might discuss about angular momentum in a little more detail. I really have not made up my mind about that, but we will see. But next on agenda coming up is hydrogen atom.